Hi everyone and welcome. My name is Jessica and I'll be your webinar host today. Today's webinar will be 2 hours long. Our subject matter expert presenter for today is John Ross Cromer. Before I turn the webinar over to him, let's take a moment to review some basics for today's session. First, it is very important that you attend the whole webinar and participate in all polling questions. Your time in this session, as well as your participation in the polls, are monitored for proof of attendance to receive your CE hours. This is required by the accrediting bodies. If you have any questions, please contact your account representative or corporate account manager. When you joined the session today, your line was automatically muted. We do that to cut down on potential background noise and to give you the best opportunity to hear the presentation. If you'd like to ask a question, please open the Questions tab that's located in the control panel. We'll be monitoring questions, and either John or I will answer them. Also, Don will be asking you polling questions throughout the webinar. He'll explain how to answer them when the time comes. Please note that you will not be able to answer the polling questions in full screen mode. You can minimize the screen to make your answer selection. You can also find a PDF copy of the presentation located under the Handouts tab. Please feel free to download this document so you can review the material that John will be presenting today. Now, since this is a 2-hour webinar, we'll go ahead and take a 10-minute break around 1 p.m. Eastern. And regarding certificates, your certificates for today's webinar will be available in your Readthrough account by tomorrow afternoon. We'll send you an email notifying you when they're ready to be downloaded. Please notice this information regarding the accreditations for this webinar. If you have any questions, please contact your account representative or corporate account manager. Thank you for your attendance and participation in this session. As I said, today our subject matter expert and presenter is John Ross Cromer. At this time, I'll pass control of the webinar over to him to get started.
All right, welcome everyone. Just some real quick background on myself that I think is, you might find interesting. I recently changed jobs. So for the last 12 years, I've been working in the solar industry as an installer. I recently took a job doing technical support for a battery manufacturer outside of Philadelphia called Fortress Power. We do lithium iron phosphate battery solutions for commercial and residential. And that is, it's like drinking from the fire hose in terms of learning about, where the battery industry is right now. So it's a fun industry, emerging industry, and will quickly eclipse solar in terms of revenue and project sizes. So it's a fun industry to be in, and feel free to ask, solar or battery questions throughout this program. We only have 2 hours today, so might as well get started. I have put my email address in the chat room. So if you want to send me an email, make sure to take note of that email address to send me questions or follow-ups. I don't mind giving out things like, recordings of the presentation or answering any questions following up. So I don't know if any of y'all took the program last month with Red Vector, but this is kind of a continuation of our exploration of National Electric Code. So we had a 2-hour class that was kind of a crash course read through of the early sections of National Electric Code last month. And what we're trying to do, no audio. Okay. Can someone comment in the chat if you can hear my audio? Got it. Hold on 1 second. Okay, guys. Okay, so John, other people can hear me fine, so I'm gonna head and keep going. But yes, absolutely. If there are technical difficulties that you're having, do say so immediately, because you know how these webinars can go. But at any rate, National Electric Code is organized so that there's general sections at the beginning, and then there's specialty sections, moving on towards the, moving on in. And so what we're going to talk about are the portions of electric code specifically to solar and batteries today, to better understand the design principles involved. specifically focusing on Articles 480, Article 690, interconnection. And what's kind of interesting about batteries is that there's two sections in National Electric Code for batteries. There's 480 and then there's 706. So we will start out with 480. Pretty simple. So let's go ahead and just get started. Okay, so we'll start with a polling question. This is where y'all need to help me because this is how we track your activity uh, during the program. And so if we answer the polling questions really quickly, then they're not going to take that much time and we can spend more time on content. So generally speaking, we need to get 90% of the viewers to vote to move on. And so the faster y'all just answer these polling questions, really to log your participation and let us help me know your skill level, the better. So throughout the 2 hours today, we will have a 10-minute break at the top of the hour, but we need you to answer these poll questions so that we can, go ahead and go. So this one, we have 91% voted. How experienced are we at battery projects? And go ahead and share the results. We say, most of our audience, half our audience, none at this time. A quarter says some interest, and a small portion saying we're using with some solar projects. What's interesting to me is not all battery projects are solar projects. 3/4 of the California self-generation incentive program is 3/4 of their battery projects are battery only projects. Batteries have applications and value that solar does not, particularly with commercial application and demand management. So you don't always need to have solar attached to a battery. And maybe this isn't the most noble of arguments, but in many cases, what the solar array does is yes, it'll help you during a blackout to have some on-site power generation in addition to storage, but the maybe more motivating factor for adding solar to batteries is that if you charge your batteries with a solar array, it'll qualify for the federal tax credit. So I don't know if that's the most engineering. Let me go ahead and hide this polling question. I don't know if that's the most engineering appropriate design consideration, but in the market, that is what we see happening. So batteries and solar panels are similar in that they both are comprised of a series of cells. And in National Electric Code, you'll get definitions of cells, kind of the base unit of the battery. Electrolyte, it's the fluid between your cathode and anode. Terminals being what the cathode and sticks up out of the cathode and anode out of the battery that you ultimately attach onto. We have an information note that lead acid is at 2 volts and lithium ion is at 3.6 volts to 3.8 volts. Often technology will outpace National Electric Code, and within the battery industry, with just like with lead acid, there's a couple of different types of lead acid. In the lithium ion battery industry, we have primarily lithium cobalt batteries and then lithium iron phosphate batteries. Lithium cobalt has higher cell voltage, 3.6 to 3.8 volts. Lithium iron phosphate has a slightly lower cell voltage, and that results even when you wire all these cells up to make a 48-volt battery, technology for technology, cell for cell, that lithium iron phosphate at a slightly lower cell voltage will have a slightly lower operating voltage for the same number of cells than lithium cobalt. Lithium cobalt's like the Tesla battery. Lithium iron phosphate is almost what everyone else is using. Um, and what that means is you'll have different, voltage charge settings, with lithium iron phosphate being a little bit lower voltage. So we will have, a 2-hour program just on those nuances, more of a design program later on, but this is our electric code class, so let's stick to electric code. So section 480 is kind of what the traditional battery section was before we start getting into higher voltage batteries. Commercial batteries can be, 400 volts, 500 volts on up, even into 800 volts. So the section 480 is more general battery requirements, and it is then expanded on later on. So let's learn the general requirements, then we'll get to the more advanced section towards the end of the program. Okay, so storage batteries and battery management equipment shall be listed. Um, this requirement shall not apply to lead acid batteries. So, basically what this is saying is as the market moves towards lithium ion batteries, we will see an increased focus on listing requirements. And we'll talk more about that in a couple slides. We have overcurrent protection for prime movers. So overcurrent protection shall not be required for 60 volts or less if the battery is for starting, ignition, or digital control of prime movers, like starting a generator. We're talking about batteries that are not for prime movers, and so your overcurrent protection requirements for general circuits apply to batteries. What's interesting to me is there's right now an electric code, and I imagine this will change quite soon in the next update, or NEC 2024 or 2023. I don't know any of the discussion, but I imagine there'll be a clear call out for overcurrent protection in line with your battery banks. But as it stands, if your batteries are kind of like tapped onto your battery conductor within 5 feet of the battery itself, there's no specific mandate for overcurrent protection in your battery circuits, although it is a very good idea to have that. I suppose if you're buying batteries that have, more features built into them, like, often you'll get batteries that have built-in controllers. These controllers can get quite advanced. These controllers often will already have fuses and relays built into them for protection from overcurrent protection. So adding external overcurrent protection can be redundant. At this time, it's not necessarily a mandate for these battery circuits to have overcurrent protection if they otherwise are not required to have overcurrent protection. Essentially, when the battery circuits start to get long in length, you want to put overcurrent protection in line. But what that also means is there's no additional requirement for external overcurrent protection. And so if you have a battery that has built-in current protection circuits built into it, then you're fine. Although it's still not a bad idea to put additional overcurrent protection in line so that the fuse that is external would burn up before any internal fusing inside the battery pack would. Let's talk about the DC disconnect. We have to have a disconnecting means for all ungrounded conductors coming out of a battery with a voltage of over 60 volts. So many battery banks are 48 volts nominal. And so the disconnecting means is not required right off the bat for the battery, although as we'll see later, pretty much whenever the battery is more than 5 feet away of where it's being plugged into, you need a disconnecting means. And then it's also, just because you're not required to have a disconnect, it's still a very good idea to have a disconnect. If you want to service the equipment and de-energize the equipment, the disconnect is there. So, what is this telling us? Well, often, the commercial batteries on the market today have built-in disconnects, like a push button switch to turn them on or off. And if they're located right next to the power electronics that they're connected to, they don't necessarily have to have an additional disconnect built into them externally. Those requirements only come into play when you get into, I don't know, if the electronics are far away, if they're in adjacent rooms and the conductors are going into the room. For example, if you have your batteries located outside the building and then your inverters are inside the building, it goes through a wall. At that point, you need to have a disconnecting means. And so we get to item B, and it says where a disconnecting means is activated via remote control, and the controls for the battery disconnects are not within sight of the battery system. Whatever disconnecting means you have needs to be locked in the open position. So, if someone could be remote controlling the battery disconnect in another room, then where you're required to have a battery disconnect, and that would be one of those cases, the battery disconnect needs to be able to be locked in an open position. So generally common sense stuff. Let's see. The disconnecting means shall be legibly marked with nominal voltage, current rating. Here's one of our batteries at Fortress, and you can see we have a built-in breaker into kind of our battery pack. That's just a traditional 250 amp breaker at the top of the battery. And that would meet all of your code requirements without the need of having an external disconnect switch, which is a common requirement for solar, for example. So, and again, the battery industry is still in its infancy. And so I imagine these requirements will, I don't know, become better filled out in the future. Okay, so here's one with battery support systems, is like racking that battery sits on top of. And as a information note, the electric code that you see up on the screen, I'll have sections of the code chopped out of it. Or if we're talking about tables, I'm not going to provide the full table in the program. And that's not a decision I've made. As we talk in our intro to code class, code is owned by a private organization, and it's paid for by people going out and buying copies of electric code. So you can't just print out electric code word for word, even in a presentation. It's really supposed to be referenced by direct reference only in casual discussion. Within the context of continuing education, just having the code titles and nothing else is a little, not counterproductive. But at any rate, if you're frustrated that I'm not giving you the full code word for word in this class, it's not my decision. Anyway, back to support systems. For battery chemistries with a corrosive electrolyte, the structure that supports the battery shall be resistant to deteriorating action. So batteries are heavy. When you're building a battery room, you put them on a shelf, on a rack, and often, more likely than not, that shelf or battery rack is built out of metal. So it's like, well, hold on, I'm putting something that's very conductive on a metal support structure. I remember on one of my first battery projects, these batteries are very heavy, and we were picking them up with our on-site lift equipment by attaching some metal chains to the metal casings of the batteries. And the battery terminals are just sticking out, right there. And what we had to do was we had to tape the chains with some like rubber resistive tape to just actually chain the batteries to the lift equipment to pick them up and move them around. Otherwise, we'd get arcing between the battery terminals and the metal chain that could continue to conduct into the metal lift equipment and potentially electrocute the driver. So, you know, the takeaway here is that metal racks for batteries are not good enough. The racks have to have some insulative properties to it. What's interesting about that is concrete is considered to be conductive in the sense that if you have you know, a concrete slab or a concrete wall in a basement, if when it rains and the soil around it gets wet, you know, the concrete itself gets wet and it can become conductive in those circumstances. Likewise, you can have you know, some voltage creep out of a battery, and if it is on a metal rack, you know, potentially you can have the rack be energized and that be a safety hazard. So what do we do in that case? Well, we have to use rubber mats. You know, if you're putting the batteries directly onto a concrete slab, that support structure has to be non-conductive, so you have to put a rubber mat between your battery and the concrete slab. You don't want to forget that step because these batteries are very heavy and picking them up is not something that is particularly easy to do. Here is a battery that is designed for floor mounting, and it has a insulative kind of hard plastic base so that it can be just set right onto that concrete slab. Similarly, you would put a rubber mat on your metal battery rack, or you know, maybe a anodized metal is more resistant. So painting the metal rack alone is not considered insulated battery rack. You know, let's talk about ventilation for a minute. I guess simply there are sealed batteries and there are unsealed batteries. And unsealed batteries, like traditional flooded lead acid, that, you know, they produce gas as they're being charged or discharged, and that gas needs to be vented to the outside. Okay, easy enough. The question becomes, does a sealed battery also need to be ventilated? You know, you could say, well, you know, that's a great advantage of having a sealed battery is that you don't need that ventilation. But the problem becomes, what happens when a sealed battery becomes unsealed, and let's, for discussion purpose, say through no fault of the battery itself. You know, let's say the building's on fire and the fire makes it to the battery room and the fire starts burning up the casing of the batteries, and it heats the battery to the point where it catches on fire and all of a sudden the battery's on fire. You know, in that case, what was a sealed battery becomes a unsealed battery. And so there has been one industrial battery fire in I believe it was Arizona, it was APS, where it was actually the battery itself. As far, I'm not sure if the investigation is complete yet, but you know, not many suspects in this fire to begin with. You know, the battery goes through some internal failure, it catches on fire, and all of a sudden it's leaking gas into the room. And for whatever reason, and I don't know the real details of this, so just hypothetically speaking, if you have your ventilation going in your battery room, but it's an emergency and your ventilation is not on some kind of emergency or backup power circuit, and so your ventilation isn't working when the fire is going on, you can get gas accumulation inside that room. And that's exactly what happened in this APS fire. The batteries caught on fire, the room was not ventilating, and the gas accumulated inside the battery container, when the fire department showed up, as soon as they opened the door, the room exploded and it sent a bunch of firemen to the hospital. No one died. I think one person had serious injuries, the fire chief who opened the door. And so what we're going to see is that as the sealed batteries get larger in size, the ventilation requirements become mandatory even with a sealed battery. So the takeaway from this is that you can't just assume that the battery room does not need to be ventilated simply because you have a sealed battery. So these ventilation requirements are actually going to be better detailed in other parts of fire code, not National Electric Code. And so we see National Electric Code referencing fire code for ventilation of larger battery banks. Okay, so let's get into polling question 2. So the polls are now open. So let's go ahead and vote. Thinking about your own house, where would you want to fit the battery? And so my preference for batteries are for them to go inside. Batteries, particularly lithium batteries, they have a temperature extreme that they can tolerate. You can put a battery outside, provided that it's shaded. And batteries can get down into to right down to freezing. I think lead acid, even lead acid, when you get below freezing, has degradation. So maybe it has a slightly larger temperature range tolerance than lithium ion. But the point is that if you use a battery within its listed temperature range rather than its preferred operating range, which is much more narrow, exposing your battery to these temperature extremes will get a shorter life out of it. And batteries are expensive. You want a long life out of it. At the same time, I can understand where customers come in and say, well, I do not want batteries inside the house because of the potential for fire hazards. Lithium iron phosphate has a much higher tolerance to heat than lithium cobalt, so there are some fire safety nuances. But the garage is a very common place for a battery. And outside the house, you can find batteries that are NEMA 3R, and in fact, one thing that we're looking at for kind of our next product design is having liquid cooling systems built into the batteries so that, they can just be placed outside the house on a concrete slab and still heated and protected from the environment. And so we'll get into, let's close this poll, and then we'll talk about these a little bit further. We'll go ahead and share it. And so I don't think you're wrong on where the right location is for the battery. It's possible to put them in the house. I think the best location for a battery is inside, in air conditioning, in a dust-free environment. Just like other solar electronics, you'll get much better life and performance out of that. To me, dust is as bad as anything else in this consideration. The garage is common. Outside the house is common. Inside the house is common. Let's talk about this a little bit further. The main thing is live parts operating at 50 to 1,000 volts nominal. And this is squarely within the realm of home battery banks and even I guess lead acid has 48 volt nominal. In the lithium ion industry, we'll refer to a 48 volt battery bank as a 48 volt battery bank. But if you open up the spec sheet, you'll see that its resting voltage is closer to 50 volts. Our batteries our 48 volt batteries on the spec sheet are read as 51 volts nominal. Live parts operating at 50 volts to 1,000 volts nominal shall be guarded against accidental contact by approved enclosures. So I've done battery banks in battery rooms where you walk into the battery and you see the exposed terminals, and the customer says, well, if I touch those terminals, am I gonna, shock myself or electrocute myself? The answer is yes. These batteries, energy storage devices, they do have an element of danger. And so these, anywhere from your home batteries to your commercial batteries, they need to be protected. And so that's either you're buying the battery itself and then assembling a system, or you're buying a manufacturer assembled system where all the exposed parts are protected, or it's something in between the two where you're buying manufacturer A's battery and manufacturer B's inverter, and you still have to wire them up together. And so depending on what kind of battery you get, you might have exposed terminals or not exposed terminals. Those exposed terminals need to be guarded against accidental contact by approved enclosures. And so that means that you can't just go buy the cheapest battery on the market and put it on a shelf in your garage. If it has exposed terminals, you're going to run into different design considerations than if those terminals are enclosed in a case that's provided by the manufacturer. So if you do have exposed terminals on your batteries, what do? Well, the location can only be accessed by qualified persons. Does that necessarily mean you have to have a locked battery room? No. It's a good idea to have a dedicated battery room that's locked, but it's also common to have, a cage inside a garage that is a locked cage to prevent people from getting into the square footage of where the batteries are, but isn't necessarily a dedicated locked room. So you could have your exposed terminal batteries as long as they're caged off, or what is far more common is, to buy kind of a higher end manufacturer assembled system where the battery terminals are already protected by the, I guess, battery assembly itself. You can elevate the batteries above the floor. 8 feet is the typical one. If you elevated them less than 8 feet, then you have to treat it kind of like a locked cage. So, basically, if you want to put your batteries in the garage and you're buying kind of just the battery and not something more top shelf, you're going to have to cage it off. So do-it-yourselfers be warned, you can't just buy a homemade battery with exposed terminals and keep it on a shelf. You'll be liable for that. If you're going to build your own battery pack and keep it under 50 volts, and even just playing around with it with do-it-yourself kind of stuff, you need to secure the immediate location and make sure that secured area is dedicated space. Okay, so spaces around battery systems. You need to have a 1-inch clearance between the cell container and any wall. And so how this is actually going to play out is that we're going to get into differences for a completely enclosed battery inverter system, like the Tesla Powerwall, which has its own battery and its own inverter, completely enclosed in one shell. And that just can be mounted directly to the wall, versus a battery that's more like what you might think of as a car battery, just a big block with exposed terminals coming out of it. And you are allowed to build your own, battery assembly. Yeah, it's a process that's been going on for years and years, pre-Tesla era. And there needs to be a 1-inch clearance between the cell container and the wall. And so you'll see, battery mounting brackets that will, separate the wall from the battery when you are wall mounting your batteries. Or if you're floor mounting the batteries, you can't just butt them up against the wall. They're not permitted to contact that adjacent wall. Even the shelf itself will have this clearance requirement, and we'll reference that a little bit later. The terminal clearances, how much vertical space you need between the battery and the shelf above it, that is something that's driven by the manufacturer spec. So that's not a clearly defined vertical clearance in code. If you are putting your batteries in a battery room, you want that door to open outwards rather than inwards. And once your batteries get over specific voltage, and we'll see this in the battery section, more advanced battery section, the doors need to have panic hardware so that you can't get locked in to a battery room, even though it needs to be a lockable door. Gas piping is not permitted in dedicated battery rooms, so keep that in mind with your electric water heaters, your utility room planning. And then another one that is it should seem obvious, but illumination is required in your battery rooms. And so where that comes into play is, I did a project where we put the batteries kind of outside the building, but the home was on a hillside, and we had a little alcove that we could put the batteries into, kind of tucking them kind of up against the building foundation in their own little dedicated space. Well, that little dedicated space, if it's not just a box that you're standing outside of and then working into, if it's an actual battery room, that battery room needs lighting. So if you're building a battery room adjacent to the building, it can't just be four walls and a ceiling. It needs to be a little bit more professional. And all of your working clearance requirements apply that you see in the earlier sections of code, such as vertical spacing and clearance behind you. Basically, in a dedicated battery room, if your batteries are in a room, you need to be able to fully stand up in that room. You're 6.5 feet of vertical clearance, and anywhere from 3 to 4 feet behind you before you get to the next wall. So these battery rooms have to be rather sizable and professional. If you don't have enough space for a battery room, build a battery box instead. Don't build something that's halfway a room. Don't build a battery box that is so large that it's really a room. If you're really building a room that you have to go inside to work on the battery with, then it needs to be a proper room. Let's see. I guess we were talking about 480, but this is kind of a code review. And so there's in this adjacent section to 480 with batteries, we have 460 for capacitors. I think what's really interesting about capacitors is that in most national electric code, in your battery circuits, when you're sizing your cable, you're looking at the ampacity of the battery circuit, and then you're adding 25% additional headroom for that. And there's differences between continuous output that's running full time and intermittent output that is maybe running for under 3 hours or less. And in the beginning parts of code, we see that a lot of stuff is sized to be either 100% of the intermittent output, the discontinuous output, or an additional 25% for continuous load. With capacitors, it's a special thing where they say the conductors have to be 35% rather than 25%. And so as a building engineer, with solar and batteries becoming more prominent, you may find yourself needing to take a master electrician exam, for instance, and you say, well, what are all the sizing considerations? Typically, you're oversizing your conductors by 25% when it comes to electrical design. There are special exceptions. Solar is one of them. We'll talk about why a little bit later. Capacitors are another one of them. Capacitors get a 35% oversizing. And I believe that's just because capacitors can be so rapidly discharged. Okay, so that's pretty much it for section 480. It's a very short section, and most of the robust battery requirements are being migrated towards the more specialty sections towards the back. And so with electric code, kind of the general rules sections end at chapter 4, and then we get to chapter 5, we start to get into specialty requirements. So chapters 1 through 4 are to do with services and feeders and the wires and cables themselves, and then general equipment like air conditioners and lights and dishwashers and appliances, stuff that's just all over the place. Chapter 5 onward starts to get into specialty applications and special occurrences, which we don't, that's not the scope of this class, but if you were in our previous program, now we are getting a more comprehensive introduction to electric code. So now we're into chapter 6. Let's do a quick polling question to kind of see where our solar experience is. I'm going to go ahead and launch this polling question. So let's go ahead and vote. Yeah, so a lighting fixture can be a regular enclosed light. Often in a battery room, it is not terrible just to have the lights be battery powered and just turn on little light strips glued to the ceiling is a cheap and pragmatic way. I've been living in Mississippi for the last 5 years. We do things a little bit lower end. When you're doing lighting considerations in a battery room, you might want to consider having them be on their own kind of dedicated circuit. Same with ventilation. It's not a bad idea to have your ventilation and lighting be on a backup circuit and not just pulled off your main service panel, so that if there is something that's going wrong and you're having to take your system offline, you still have your critical load circuit or backup power circuit energized and servicing that room specifically. And for that reason, maybe this is a good reason to have a cheap stick-on external light with its own battery in the battery room itself, so that you can take your whole building's power system offline and still work in that maintenance area uninterrupted. Things do go wrong, so you want to be prepared for that as much as you can. Okay, so let's close this poll and we'll share it. And so we have a few solar veterans, most casual solar exposure, and then some with limited solar experience. So, all right, let's go ahead and continue. And just through our journey, we're making our way to section 690, but we have other examples of special, chapter 5 was special locations like boat docks. Chapter 6, we get into special equipment. We have electric vehicle charging stations. They say, hey, there's ventilation requirements for your garage based on the amperage ratings of your electric vehicle chargers that will drive ventilation requirements for your garage. Okay, so section 690. This is the solar section. I think the first, right off the bat, we get into definitions and we get this really confusing term of functional grounding. It says, a functional grounded system is one that's connected to the ground through a fuse, a circuit breaker, that is part of the listed ground fault protection system. Conductors in these systems that are normally at ground potential may have voltage to ground during fault conditions. It's kind of a confusing term and definition. What this term is really here for is that we've had a change in inverter architecture, whereas more traditional, like early 2000s and earlier solar inverters were, and most battery inverters on the market today are negatively grounded inverters. And what that means is on the DC side, they would take the negative side and tie it directly to ground, and that makes sure that your DC side, you have a positive side and you have a negative side. And so on that negative side, they would ground connect it directly to ground and keep it pegged at that 0 voltage ground potential. But how DC really works is you have your positive side and your negative side, and on that 12-volt battery, you have 12 volts of potential between the two. And so if you don't connect your negative to ground, you still have 12 volts between your positive terminal and your negative terminal. It's just now that negative terminal does not have a direct reference to ground. And so the problem with negatively grounded systems is that it creates a blind spot in the ground fault detection. In very limited circumstances, you could have a ground fault on a negatively grounded system that is not detected by the inverter system itself. And so, and it's not really a hazard until other things start going wrong. But that's generally how hazards become major hazards, is if they occur and then the control systems that are designed to protect them fail as well, allowing the problem to continue. And so what was happening with solar arrays, particularly commercial solar arrays that are dealing with lots of power and lots of circuits, is you would have thermal expansion. And this is what happened. There was a fire in Bakersfield, California, and then another, and by now it's still a 10-year-old fire, but the Dietz-Watson fire in New Jersey. What was happening is installers were failing to design around thermal expansion up on the rooftop. And so for very long exposed conduit runs on the rooftop, thermal expansion was pulling apart the conduit. And even if the conduit was otherwise properly installed at the beginning of the project, if you don't account for thermal expansion, that the pressure on the connectors can pull conduit out of the connectors, then you have sharp conduit edges biting into the cables that are inside them, and you're having ground faults occur. Well, normally your inverters have ground fault detection, but then you had this negative blind spot in the ground fault detection of these negatively grounded inverters. And so the solution was, well, we're going to stop doing ground fault detection with negatively grounded inverters. We're going to have what's called a floating inverter. And the difference between a floating inverter and a negatively grounded inverter is you no longer have that negative to ground direct connection. Instead of just fusing the positive sides and having the negative side tied off to ground, you now have fuses on both the positive side and the negative side with no direct connection to ground. And that was causing inspectors to be like, well, okay, so now we have this ungrounded inverter. And say, no, you still have your equipment ground conductor. The inverter is still functionally grounded. We're just no longer tying that negative side into the ground. So, don't get too confused by this term at the start of chapter 690. Just to say, we do have inverters now that are called floating inverters, but they're still grounded. You still wire up your equipment grounding conductors to them. Generating capacity. So this is kind of interesting. The generating capacity is the inverter output in kilowatts. So on your interconnection agreements, it says the size of the system. The traditional, if you're asked on a permit document, what is the system size, and it's not telling you specifically if it's referring to the size of the DC input or the size of the AC output, the generating capacity is based off the AC output. Let's see. One more polling question. This is, what is the maximum voltage allowed? And this is a trick question, by the way. All right. So what is the maximum voltage allowed in a battery box that is detached from a house? So this is a tough question. Most people are getting it wrong right now, but let's see where the reason I'm putting in this question is that you might have a solar array, let's say in an off-grid cabin, and the cabin is in the middle of the woods, and there's a field that's 1,000 feet away from the cabin. So the site for the solar array is really far away from the location of the house. And what you might think is like, well, what do utilities do when they're transmitting electricity over really long distances? And the answer is, well, they step up to really high voltage. Because as you increase your voltage, you're decreasing your amperage, and voltage is more constrained by, say, the jacket of the cable, and you can be fine right up to 600 volts, but if you have a 600 volt device and you go a couple volts more than 600, it'll pop, almost like bursting of a water balloon. Whereas amperage is more of a slower burn. If you exceed the amperage of the system, the device might not fail immediately. It just might run hot, it might start to smolder, and then it might catch on fire, but it's not an instantaneous kind of disaster for a slight over amperage like it is over voltage. And all this is to say, power is volts times amps. If you're doubling the voltage, you're cutting the amperage in half. And the thickness of the cable has more to do with amperage than it does with voltage. And so when you're transmitting electricity over a very long distance, you're stepping up to high voltage to reduce the amperage so that you don't need as thick of cables. And so that's why, in our power grid, when we get into distribution, we have, 10,000 volts distribution circuits and getting into 100,000 volts and more on transmission side. Let me go ahead and reveal the answer here. And so you might ask yourself, if my solar array is really, really far away from my point of use, should I move to a higher voltage platform to do so? And so it's common in residential when you're on the building, you're constrained by a 600 volt limit. So residential solar products are at 600 volts. Commercial buildings don't have that 600 volt constraint. They're with 1,000 volt. And then when you get into utility scale, they don't have that 1,000 volt constraint. They can go up to higher voltages, and you'll find 1,500 volt appliances, or not appliances, applications. Your standard solar cable and most of your solar panels are rated for 1,500 volts. And so you might find yourself designing an off-grid cabin where the array is really far away from the site, and you think, well, can I use some utilities, treat my ground mount like a utility scale array and run high voltage lines? The answer is yes. There's some additional constraints, mainly to do with site security. You'll need to fence off the solar array so no one can get into it. But if you're already building a secure battery box and you put a lockable fence around your solar array, you can do a 1,500 volt design if you want to, even though it's a residential property, as long as the array is detached from the house. So if you're detached from the house, you can be over 600 volts. If you're attached to the house, you have to be 600 volts or lower. Now, most battery systems are at 48 volts, but not all. The Tesla Powerwall, for example, and then let's see, there's a popular solar inverter company called SolarEdge, and they've partnered with LG, and they make a higher voltage battery. A lot of commercial batteries are at higher voltage too, and for reasons we just discussed. The higher the voltage, the lower the amperage. And traditionally, the battery inverter industry is at this 48 volt platform. But the problem with that is the lower your voltage, the higher your amperage, the thicker your battery cable. And so by the time you get into whole house applications at a 48 volt platform, the cables coming out of these batteries are having to be rated for 350 amps. Your electric service panel is rated for 200 amps, but that's at 120 volts or 240 volts. So if you're supplying, even though it's DC versus AC, if your home is 200 amps at 240 volts, and then you're going on to a 48 volt battery, your amperage is increasing. And so, long story short, this 48 volt architecture is fading away from the market, even though the vast majority of residential battery systems on the market today are at a 48 volt platform. You're starting to see 380 volts, 400 volt, nominal batteries that have voltage ranges from 150 volts up to 550 volts, similar to a solar array. We're seeing more high voltage products come to market, and I think that's ultimately that's for the best, to the point where it'll become a standard. Okay, so a couple more things, and we're going to take a 10-minute break. On 1 or 2 family dwellings, your circuits have to stay 600 volts or down. On other type of buildings, 1,000 volts or down, and then otherwise you're looking at 1,500 volt circuits. All right, so the next topic starts to get into solar circuit designs. So with most battery circuits, you take the battery amperage and then you add an additional 25% headroom. But solar is more impacted by temperature than other electronics. And that's for a few reasons, but it's the top of the hour. So just to keep on time, let's take a 10-minute break. A 10-minute break, everyone. We're going to start right back up at 10 after, but it's 1 o'clock Eastern time right now. Let's take 10 minutes off and then we'll pick back up in a little bit. So 10-minute break. Now's a great time to ask questions, even tough ones. A 10-minute break. We're going to pick back up at 10 after. So we're going to pick back up in about a minute or so. Okay, everyone, welcome back. We're now into round two. We're going to get a little bit more accelerated and a little bit more advanced here. So let's expand our solar design understanding. When you look at a solar module specification sheet, and it's a 300-watt solar panel, it's really down here in the fine text at the bottom, but that 300-watt listing is done at a standard test condition. And that standard test condition is not a particularly good one in the sense that it's done at a temperature, and it's not just an ambient temperature, it's a surface temperature of the solar panel itself is at 77 degrees Fahrenheit or 25 degrees Celsius. 25 degrees Celsius, 77 degrees Fahrenheit surface temperature under full light. And of course, the definition of full light changes too, because it's different on a humid day versus up on a mountaintop. It's different in the morning than it is at high noon. So the 300-watt test condition of solar is not what that solar panel typically does out in the field on a day-to-day performance. And so this is where that standard 25% adjustment for additional, say, amperage allowance, just like we saw capacitors, because of their unique technology being incredibly rapid discharge, are given a higher safety factor for amperage allowance. Solar, we have additional temperature correction factors that are special for solar that get applied. And often these temperature correction factors are found, right on the spec sheet of the module. But within most solar modules are made out of silicon. Pretty much all solar modules that are going on a rooftop are made out of silicon. And even though you might have slight differences between a monosilicon panel or a polysilicon panel, we're really splitting hairs here. Silicon has similar characteristics regardless of the type of silicon used. And so we have a temperature correction chart that's built right into electric code that gives you an assumption factor that says we're going to assume the temperature correction factor is this. And so you look at the operating conditions of the array, and then you apply these temperature correction factors, and they have them for amperage, they have them for voltage. A volt times an amp is a watt. So there's also one for the combined two, the power. And so the way these work is they're given as a percentage per degree Celsius. So for every degree Celsius you deviate from 25 degrees Celsius, for every degree Celsius you deviate from that, you add or subtract a percent of that voltage rating or that amperage rating or that power rating. And so what we see is the temperature coefficients of power is a negative sign, and that means for every degree Celsius above standard test condition, above 77 degrees Fahrenheit, the hotter you go, the more the power of the solar panel decreases. Oppositely, the colder you go, the more the power will increase, assuming that it's the same amount of sunlight. The only reason that solar is less productive in the winter versus the summer is that there's also less sunlight. So, it's colder temperatures, which are good, less sunlight, which is bad. In fact, your peak power will come out of your solar array in the springtime when it's nice and sunny, but also chilly. In the summertime, you'll get more energy, but energy is not the same thing as power. Energy is power over time. So in the summertime, you'll get less power at high noon from the array, but you'll also get more energy because days are longer. So the array operates for 10 hours instead of 6 hours. Not 10 hours at full capacity. There's less in the morning than at high noon, but regardless, we have to adjust for the impact of temperature, and we do that by looking at the temperature it is outside compared to the standard test condition and applying a percent degradation factor because of that. So let's look at these temperature correction factors for voltage versus amperage. The voltage one is a minus 0.25, whereas the amperage one is a positive 0.03. So the voltage is an order of magnitude greater than the amperage factor. And what that means is voltage is more impacted by temperature than amperage is. So amperage is impacted by temperature, but not as much. And it also means that voltage decreases at higher temperatures and increases at colder temperatures, whereas amperage will do the opposite. Amperage will increase at higher temperatures and decrease at lower temperatures. And so if you are putting in a fuse on a solar circuit and you undersize the fuse by accident, it's most likely to blow in the summertime, because fuses are based off amperage and you will reach your maximum system amperage ever so slightly in the summertime. Whereas you'll get to your maximum system voltage in the wintertime when it's cold out. So how that relates to solar design, very briefly, because nowadays all this stuff is done by design software, but you put in the manufacturer design software, you put in your location, and then you're designing around your coldest temperature. And then on the hot end, you're not going with, like, often, and your inspectors will look at the coldest temperature on record in your area and say you got to design to that low end temperature, but they're not going to make you design around the hottest temperature on record, because again, that on the hot end, your voltage is decreasing, so you're not going to have a problem there. And then even though your amperage is increasing on hot temperatures, it's not increasing by very much. And so it's more the pain point in your design is the coldest design temperature on record, making sure that your system stays below, well, if it's a residential project and it's on a building, making sure your system stays below 600 volts. And so your design softwares are taking in the temperature correction factor of the solar panel itself and making sure your circuits don't stay below 600 volts. And so you put in what inverter you're using and you put in what solar panel you're using, and it essentially tells you, how many solar panels you can have on a circuit based on those temperature correction factors. That's pretty common to any solar design software. And so what that means is if you're in the northern half of the United States where you get into colder weather, you might not be able to have quite as many solar panels on a circuit as you could, in the southern half of the United States, because they don't get down into that colder design temperature, so the voltage doesn't rise on the circuits on the roof as readily. So when we get into maximum voltage on a circuit, basically you have to adjust by these temperature correction factors. But we're seeing code is starting to drive a difference between just having DC to DC modules in series versus having DC to DC converters in series. What is that? What does that really mean? We'll get to it in a minute. What we're seeing here is basically you take say for current, you take the number of parallel circuits, because in parallel your current is adding up, and then you add a 25% correction factor to it. Often, whether or not it's calculating the voltage with your temperature correction factors, or calculating amperage, the main difference is that engineers can come in and say, well, actually, the coldest temperature on record happens at 3 a.m. at night, and the solar array is not going to be on by the time the sun comes up. It's only, it's no longer -40, it's -20. And so I'm an engineer signing off the project. We can do the design around -20 instead of -40. National Electric Code is fudge factors so that electricians who aren't engineers can do the design work in a safe manner. But electric code almost across the board allows an engineer to step in with a calculation to say, I'm gonna do the math for real, and that's gonna give me a little bit, less of a design constraint than using the fudge factors. And so here, when we're calculating solar module circuitry, we take all of the amperage of the modules, and then we add 25% to it as an additional safety factor. Whereas an engineer can look at that day of maximum production expected and not use the extra 25% allowance. And so then we get into the circuit sizing. And this is where it gets a little confusing, because most circuits in National Electric Code, when it comes to conductor ampacity, you're taking the continuous output of the device, you're adding 25%, and basing your calculations off that. But what the solar specific section says is you take your total, your total output, and you add 25% to it, and then you add an additional 25% to it. And why is that? Well, it's because your solar array is listed at standard test condition, and in reality, out in the field, there's going to be days where it's performing well above standard test condition, and we need to take allowance for that. So either an engineer is going to have to step in and say, this is what the array is really going to be doing at max production, or we size an additional 25% onto that. So whereas most circuits in a building have a 25% headroom solar circuits have an additional 25% headroom. That brings the total to 56%. 25% times 25%, or times really 125 times 125. But anyway, the exception to that has become standard in solar because we're not letting the solar conductors just run on a roof unregulated anymore. Back in the day, you just click the modules together, say, let's expose it to the elements, the temperature, the solar array can run uncontrolled. And so we have to have not just a standard 25% oversize, but an additional 25% oversize. But today we're installing these electronics behind every solar panel on the rooftop that do things like regulate and adjust the amperage and voltage of the circuit. These are called DC optimizers. And when you're using these digital controllers behind the array, you don't need to use that additional 25%. And so on a DC optimizer array, your conductor ampacity is just an additional 25% of the continuous output rating of the circuit, whereas without optimizers, without these module level controllers, you have to oversize by 56% rather than just 25%. It's one of the harshest oversizes in all of National Electric Code, but again, that all relates to the fact that it's not just your standard, oh, we need to allow additional ampacity in our conductors so that they don't burn up, but also we need to allow additional ampacity because the listing condition of the solar panel is not what it's going to perform in the field. Whereas all other devices, a 1,000-watt microwave is going to use 1,000 watts, whether it's in Canada or Texas. Not so with a solar array. Okay, so let's just keep going over this one. Arc fault protection. So systems operating at 80 volts DC or more are now required to have arc fault detection unless it is a ground mount, not attached to a building. So arc fault detection, kind of came into being around 2014. Arc faults, we talked about in our introductory to code, they often precede ground faults. So an arc fault is a little gap in the wire, you have arcing across from the wire to the wire, whereas ground faults is fault from the wire to a lower voltage reference to ground. So if you imagine you have a power cable and you slowly pull it apart and you get a little spark between the two cables, that's an arc fault. Whereas a ground fault is you take the power cable and you connect it to a piece of metal that's connected to ground, and you're draining all the power in the cable in the ground. So in the past, solar hasn't had arc fault requirements, and solar has had this reputation for having nothing ever go wrong with it. All of a sudden, we get arc fault detection into our solar inverters, and there's a lot more tripping going on due to bad workmanship. Things like mismade connectors, they're not necessarily touching ground, but if your connector is not well seated, you'll get arc faulting across the connector. So that's detected nowadays. Okay, so now we're going to get into a new polling question. Let's go ahead and do our fifth one, and let's just see how we go. Go ahead and vote. You may not understand the question. If you don't understand, just take a guess. But how do you meet rapid shutdown requirements for your solar projects? Do you use microinverters, DC optimizers, or third-party rapid shutdown boxes? So, it's you may not understand these terms. If you don't, select no project experience. We'll see where everyone else shakes out. So go ahead and vote. We're going to close it in just a second. All right, we got a great audience today, by the way. Y'all are voting rather quickly, which is always nice. So we see ignore the no project experience. Actually, this surprises me. We got microinverters, we got DC optimizers, and then we got third-party rapid shutdown boxes. So we're going to get into what that means in just a bit. So fire departments, when a house is on fire for any reason, not just solar, one of their firefighting techniques is to ventilate the smoke out of the building. That allows them to go into the building and see where people are who need to be rescued. So that's a much more difficult thing to do if your building's filled up with smoke. Also, smoke is dangerous, and so we want to get the smoke out of the building as quickly as possible. Well, if your solar array is covering the rooftop, then the firemen can't cut a hole in the roof. And then there's the additional hazard of, that solar array is on, and by nature it's always on. If the sun's up, the solar panel's on. So the firemen get concerned about electricity from the solar array arcing into the building. Now, I think firemen should actually like solar quite a bit on a rooftop because the metal framing from the solar array itself adds some strength to the rooftop. So a roof with a solar array on a racking system on top should stay up longer during a fire, not collapse earlier than one without. A little bit of a different case with certain types of racks and certain maybe flat roof commercial systems. The takeaway is we have to consider the firemen in our designs. And so in building code, not national electric code, in international residential code, international building code, California fire code, they say you have to stay basically 3 feet off the sides, 3 feet off the top of the roof with your solar array for firemen access to cut their holes in the top of the rooftop. So 3 feet off the sides, 3 feet off the top is the general rule of thumb. Not all jurisdictions abide by this. Some jurisdictions intentionally do not abide by this because they say in our jurisdiction, there's no fireman getting up on any roof to do this hole cutting stuff. So you can go wherever you want with it. New Jersey has taken that position in the past, and then later on they've come and reversed their position. And for me as a solar installer, I like having some space on the rooftop to walk around. A solar array that is not accessible is a very difficult solar array to maintain if you ever have to maintain it. So there's a lot of reasons to give yourself some wiggle room in your array layouts. But this is really a discussion for design class. We're talking about code. So let's talk about rapid shutdown. In the past, rapid shutdown was a lot more loose. They say, well, as long as you can turn the array off outside of the array, de-energize the conductors between the array and the, where it's connected on the ground, you're fine. But ever since rapid shutdown was first, introduced to code, and I think in 2014, the perimeter has shrunk. It used to be 10 feet around the array, you could remain energized. And then it shrunk down to 1 foot around the array, it could be remain energized. But the correct interpretation of rapid shutdown today is that even inside the array, from module to module to module, you have to disconnect that module to module connection. And the reason is, well, you would still have high voltage inside the array. You'd still have 600 volts inside the array. And if the building's on fire, that 600 volt circuit is now ground faulting into the building. And whether that was the original cause of the fire or not, that's still a hazard. So we need to turn the solar panels off if something's going wrong. And so there's this home run conductor between the inverter on the side of the building and the solar array that if there's a fault in that conductor, the inverter could be turned off, but the solar panels are turned on. And so you still have that high voltage conductor that needs to be turned off. And that it doesn't matter whether that conductor is outside the array perimeter or inside the array perimeter, the high voltage aspect of the system needs to be disabled in the event of a fire. And so the way that we do that is we rely on these little boxes to go behind each solar array, or in some cases, every other solar panel, not all cases, but in some cases, every other solar panel, so that these boxes contain the disconnects to turn the modules off on command. And so back to our survey question, there's different ways to do that. Microinverters is a DC to AC product. DC optimizers are a DC to DC product. My preference is not to use microinverters or DC optimizers because these are like little computers for your solar panel, and they have very good advantages, performance advantages, optimization advantages, but there's also more parts inside them that can go wrong rather than a simple relay. So with microinverters and DC optimizers, they're nice because you get monitoring systems associated with every single panel on the roof. So you can see what every single solar panel on the roof is doing. As an installer, what I don't like is that the microinverters or DC optimizers are complicated. It's like putting a little computer, behind every single panel up on an inaccessible place of the building that's subject to temperature extremes, critters, animals, rain, ice, so it's just a lot can go wrong up on the rooftop, and I don't want, it's not in anybody's financial interest to make unnecessary maintenance trims up to the rooftop. So there's been recently an emergence of boxes that you still install behind every single solar panel or every other solar panel that don't have anything fancy inside them other than the least number of parts possible, like a relay disconnect. And that's a more simple product that still meets the rapid shutdown, disabling the array during a fire requirements without the complexity of correcting the voltage of the panel or correcting the amperage of the panel. Now, if you correct the voltage of the panel, then you don't have to have that additional 25% oversizing. So there are performance advantages of DC optimizers and microinverters. There is another option to have a more simple platform for a little bit less cost. So those there, I don't think that there's a clear leader in which one's the best approach. They are worth knowing about. So here's the rapid shutdown. It says, you have to turn off all the conductors within 1 foot outside the array. But on top of that, we're also going to limit the conductors inside the array too. And there's very few exceptions to this. The only notable exception that I can think of is if you had a completely non-metallic solar array with no exposed parts, they say, well, you have the exception at that point, like a solar shingle. But I think that's a little disingenuous because you still have high voltage conductors. And after all, these high voltage conductors don't exactly remain put when, if you have a California wildfire that puts burning debris onto your rooftop, and it's not the solar array that's caused the fire, but it's burning debris, and that burning debris burns a hole in your rooftop and continues onward. Even a non-metallic array would have high voltage conductors arcing into it. So I don't know if that solar shingle exception is going to remain in code very long. Maybe it will, maybe it won't, but by and large, most solar arrays aren't solar shingles, and most solar arrays need to have these module level control boxes, at least in the United States. It's not part of international building code, it's part of national electric code. And so we see in this picture here, there's a little rapid shutdown initiation button that the fire department, they can show up, press this button and initiate rapid shutdown to disable the array up on the rooftop. So one thing that I think is kind of interesting about this rapid shutdown stuff is it has not yet made its way into the battery conductors, where I think it makes sense for there to be, if you have fire safety, not with backup power, and you could always have, true emergency circuits on a non-shutdown, circuit. But I fully expect in the future for rapid shutdown philosophy to also be applied to battery systems, but at this time it does not. So your rapid shutdown systems turn the array off up on the rooftop, but not the battery. Maybe you don't need to turn the battery conductors off if they're 5 feet or less or 10 feet or less, but at some point, that probably will get a closer look. And so what happens is if you don't have rapid shutdown, and you turn the inverter off, you still have voltage up on the array. And even if you turn the array off, you would still have voltage in the conductors between the array and the inverter, because electricity doesn't just magically disappear. It needs to be drained off. And so the way that rapid shutdown kind of works is they press the initiation device and the modules up on the rooftop get disconnected, and then either fans inside the inverter or other kinds of load, a little small heaters inside the rapid shutdown devices themselves, they quickly consume what remaining voltage is in the conductors between the array and the inverter and burn it off within a period of 30 seconds. And so the rapid shutdown device can be kind of any kind of switch. It doesn't have to be a knife switch disconnect. There's a separate requirement for knife switch disconnects to isolate the home from the electric grid. The knife switch disconnect is also useful when the building's on fire, to make sure it's not, to make sure the building's isolated from the grid, but it's not quite the same function as the rapid shutdown device, even though your AC knife switch disconnect can initiate rapid shutdown. It doesn't have to be what initiates rapid shutdown. Okay, so there does have to be a disconnect switch for a solar array. So that disconnect switch has to be readily accessible. And a recent 2020 change is that if your main disconnect switch for the array is not outside the building already, you have to have an additional disconnect switch outside the building for the fire department. It's been mandated in almost all jurisdictions without being part of electric code for quite some time. So most jurisdictions already, you have this knife switch disconnect outside the building to turn the array off. But that's now made it into, not necessarily a knife switch, but a disconnect switch has made it into code today. So readily accessible, readily accessible means you shouldn't have to climb up a ladder to get to the place. It needs to be labeled. And that there's this 6-handle rule that applies to it. Basically, your service panels have the 6-handle rule too. And basically anything needs to be able to be de-energized by flicking no more than 6 handles. So, once you have more than 6 inverters on a service panel, you need a main breaker, an external disconnect switch, more of a general code requirement. Simultaneous disconnection. So it needs to disconnect, both the positive and negative at the same time. It needs to be marked line and load. And I probably should have put a graphic in at this point, but the number one mistake that installers make with this disconnect switch is it does matter whether or not the grid lands at the top of the switch or the bottom of the switch. And the rule is the grid, even if the grid comes up from the ground and the solar array is coming down from the roof, you might think, okay, well, I'm going to land the solar array at the top of the switch and the utility line from the bottom of the switch. And that's a code violation. The utility, the line, the supply, and it's a little weird because solar, it's not a load, it's a supply, but the main supply, the grid supply, needs to land at the top of the switch, and solar lands at the bottom of the switch. And the reason is that the top of the switch is less inside this knife switch disconnect. I think I have a picture. Well, I guess we'll talk about later because I know there's a picture coming up, but it's all about that. If you're working inside the disconnect switch, the bottom side of the terminals are easier to contact than the top. And so you want to, if that disconnect switch is thrown, one of those two sides is still going to be energized, and you want the energized side to be the least accessible side. And so the grid, the line is always at the top of the switch, with the load, or in this case, the solar array, being at the bottom of the switch. Okay, so disconnecting means basically these switches have to be manually operated. And we're talking about the main disconnect switch. You can have other disconnect switches be remote operated. Let's see, kind of getting to the wrap up of the presentation here. This is the interest of time. Can AC and DC share the same conduit or gutters or raceways? The answer is yes, but they have to be grouped separately. So generally, you'll just zip tie up the AC being separate from the DC so that they're grouped separately, so you can tell which is the AC and which is the DC. But and also you generally have to keep your functions separate. So your solar circuits cannot share the same raceway and gutters as just general load circuits. And so you can combine the AC output of the inverter and the DC input inside the same gutter. You just have to be a little organized about it. Wiring methods. So we have a couple of different wiring methods that are allowed for solar. The main thing I want to bring up here is that you can use MC cable, and we're going to talk about that in just a minute. And also, you can use flexible cable, like welding cable, that has a lot more bend to it than your fine stranded cable. Can only be used in specific circumstances. So they're saying, okay, for solar tracking arrays, you have to have a hard service cord. Welder's cable, fine stranded flexible cable, really that can only be used inside battery banks. So solar circuits have this requirement that inside the building, DC circuits, not AC circuits, but DC circuits have to be in metal. That metal is there for physical protection. So is there a real reason why AC versus DC, why AC gets the exemption? Well, no, it's really nothing more than DC discrimination. With AC, if AC had to be in metal, that would raise all sorts of questions about utility service entrance cables going inside the building without, with plastic protection rather than metal protection. Also heavy high amperage AC load circuits. They're run in Romex, and so if solar AC circuits like from microinverters needed this metal protection, it would open up a can of worms that I don't think the industry, needs to consider. That said, DC circuits, they're required to have this extra physical protection of metal, and they have to be marked and labeled. Every 10 feet, you need a sticker that says this is a solar circuit. Every 10 feet inside that building and outside that building, it needs to be marked. Access to boxes. So when you go from the array into the building, you transition through a box. That box is allowed to be located underneath the array. And the reason why you'd hide the box underneath the array, even though it's slightly less accessible, is that it looks better and it's shaded and it's protected, from the elements, from animals, from rain. And so you're allowed to put these junction boxes on the rooftop underneath the solar array, and high quality installers do, unless there's a compelling reason not to. So the array needs to be grounded. The metal parts on the roof need to be grounded. If your ground is smaller than number 6, then it needs to be protected. But you're allowed, and what's quite common is to run bare copper number 6 up to the rooftop as the ground and just land on your solar array. That's a simple way to do it. My preferred method is a little bit different than that. And we're not going to get into this polling question in the interest of time, but the question is, do you want to keep all the solar conductors outside the house, or do you want to run the conductors inside the house? My preference is to run the conductors through the attic down to the service panel rather than run the conductors outside the house. The reason is it's often more direct to go just into the attic and through. And the other reason is I use a cable for the inside the house attic run called NEC cable that makes this run expensive, but also quick and easy. And then you eliminate all this unsightly conduit, which, we were talking about fire safety earlier. I don't like the idea of metal conduit on the rooftop being exposed to temperature extremes for years and years and years, maintaining its integrity, when I could just run that into the attic and have it be a little bit more temperature regulated. Okay. So here's the junction box, and we're good. This is a specialty junction box. This is something you could do with more, generic material. And the reason you use the specialty box is it gives you a little bit less clearance. But now we're going into the roof here. And this is that NEC cable. It's called metal clad cable. And what I do is number 8 is the smallest allowable equipment ground for solar. And so I'll use number 6 NEC cable because it has that number 8 ground that's already included and protected. And the NEC gives you the metal protection. And so on my residential solar arrays, I'm just running NEC cable. Generally it's number 6 with a number 8 ground up to the rooftop. And if I'm using, 2 circuits of solar, I have two positives, two negatives, and a ground. If I have one circuit, or if I'm jumping between different sections on the roof from one subarray to another subarray with one circuit going in between subarrays, I use number 6, 2 MC cable and a ground. And this just gets strapped to your rafters, and it installs very easy. It's only the only detriments of MC cable is that it can't be installed in wet locations. It can be installed in damp locations, but what that often means is you're going to transition from MC cable to EMT. Often I'll do it right underneath the soffit, just transition to EMT and finish out the rest of my run in EMT right here. Or if it's a particularly harsh jurisdiction, I might put a box in the attic and transition to EMT in the attic itself. But that makes the installation easy and quick, and it looks nice, and it's well protected. Some other specialty parts that more of a solar installer would be familiar with are the cable glands to get in and out of the boxes. Solar output circuits should be marked to indicate polarity when connected to energy storage systems. So not just, your cables need to have positive and negative colored cable. So now we're getting into special systems. In the interest of time, we're gonna talk about the main important ones here. The first is transferring loads. So we have standby loads must be capable of supplying the full connected load for an automatic transfer switch. What's frustrating about this is that battery inverters are not large enough to power a whole house. An electric service panel is a 50 kilowatt panel, just about 48 kilowatts. Most battery inverters, most solar arrays are 8 kilowatts, 10 kilowatts. And so the idea of whole house power during a blackout with your solar array or with your battery inverter is a little bit of a pipe dream. Your systems would have to be very large and very expensive to get there, or you have to do very advanced and complicated load management to make sure that your load stays within the load of the backup power system. And so most battery inverters only back up a critical load panel rather than backing up the entire building, whether it be commercial or residential. Your battery inverters, they can be used for other things than just backup power. They can be used to kind of game your electric bill for cost savings. But in terms of that backup power capability, the code says your backup power supplies still have to adequately power what they're backing up. You can't just say, oh, well, I'm going to feed 8 kilowatts of power into my home service panel and hopefully it'll power everything, but it might not. You're not allowed to guess like that. In terms of sizing the electric service, long story short, you got two areas where you can connect to: the supply side of the panel or the load side of the panel. And so the supply side is between the utility transformer and the top of your breaker, whereas the load side of the panel is connecting where all of your other breakers are. And we don't have time to get into too many details on this, but essentially, if you count up all the breakers on your electric service panel, it might be a 200 amp panel, but you count up all the breakers, it's 300 amps. You're like, well, how is this not catching on fire? Well, if all of these breakers were functioning at full load at the same time, it would, except your main breaker would trip. And if your main breaker trips, you lose power, and the reason this all works is not all the loads on a service panel function at the same time. But if all those loads indeed were functioning at the same time, then you shouldn't exceed the rating of the main breaker. And so if this were not a load panel, if this were a power distribution panel for solar only, like on a utility scale project where you're combining a bunch of solar arrays together, you would have 200 amps of solar on a 200 amp panel. If you're doing a supply side connection and this is a 200 amp panel, you can have 200 amps of solar plugged in to these 200 amp conductors, and the power either comes from the grid or it comes from the solar array. But under no circumstance does 200 amps of supply go through the panel, because you're protected by this main breaker. But with the only thing you really have to consider is if you're plugging solar into the load side of the panel, where you could have 200 amps of power coming in from the main on 300 amps of breakers, and then your additional amperage coming in from solar, that could allow you to pull more than the service panel's rating through it. If you have 300 amps of breakers on and you have your solar array and your main, you could pull 300 amps of load into a 200 amp breaker. And so code says we're going to allow you to connect solar to the very bottom of the bus bar, but you're only allowed to have that extra 20%, and that's it. So you can, on a 200 amp service panel, you can have 200 amps from the utility and 40 amps of solar. You can have 180 amps from the utility and 60 amps of solar. But on larger systems, especially when you get into having solar and battery banks, you probably want to go and do a supply side connection, and you might want to put an automatic transfer switch ahead of that too, to kind of prepare you for off grid. So we're kind of out of time here. I got some pictures of parts on how those interconnections are made. You have my email address, so feel free after class to send me some advanced questions if we didn't get to them. But before we end, I just want to spend one more minute on Article 706. Which is the last energy storage section. And what I want to point out is the 706 only applies to circuits that are over 60 volts DC. So these requirements do not apply to 48 volt nominal battery banks. But this is where you get in, but at the same time, you shouldn't ignore the logic behind these Section 706 requirements. And this is where you get into requirements for overcurrent protection in the battery lines, and more robust requirements. And this is what we'll see in the future as we get into high voltage systems. And let's see, long story short, whenever your batteries are more than 5 feet away from their power electronics, you have to have a disconnect. If you go through a wall, you need to have a disconnect on the battery side of the wall. You always have to have a disconnect within sight of the equipment. And so just the way to keep all the, do I have to have a disconnect in mind is it higher than 60 volts? Is it further than 5 feet away from the equipment it's powered to? At that point, you need to have a disconnect. A lot of these requirements are exactly the same as what we talked about in Section 480. They're just repeats. 1 inch of clearance between the batteries and the wall. You are allowed to have the shelf of the batteries connected to the wall. It has to either be a pre-engineered system like the Tesla Powerwall, or additional space between the wall and the battery is required if the batteries are connected to a shelf that's connected to the wall. And that's the main thing to know, is that there's, when you get into higher voltage systems, you start to actually be required to put in overcurrent protection into the circuits, and you get into more spacing requirements as well. And so that's kind of the end of the program. The rest of electric code gets into fiber optic communication or microgrids, very specialty parts. The main takeaways here are that the battery rooms should be ventilated. They really should have emergency or backup ventilation so that they remain ventilated when things are going very wrong. Although that's not explicitly called out in code at this time. Equipment should be capable of disconnecting. The disconnects are required when you get more than 5 feet away. Rapid shutdown right now is not required for batteries, but it is for solar. Your labeling requirements, you pretty much have to put a label for whenever there's something special that's going on. If you're doing a load side connection, you need a label. Most sizing is you're adding extra 25%, although with solar specifically, when you're not using electronics to control the output of the array, then you have to have an additional 25%. So, a lot of ground covered, a lot of content, can't get to it all. I actually get paid to answer technical support questions all day long now. So once again, if you have any follow-up questions about solar or batteries, feel free to drop me an email and we can continue the discussion. Happy to answer your questions, fortresspower.com. And with that, thank you for coming, and I will pass it back to Red Vector.
Thank you, John. We greatly appreciate your time and expertise. So this here is our contact information for anyone who may want to have that. Once again, certificates will be available tomorrow. It will notify you by email when you can download them. There'll also be a short survey at the end of this webinar, and we sincerely appreciate your feedback. Now, on behalf of Red Vector and John Ross Cromer, I want to thank everyone for attending. We hope to see you again at a future webinar. Thank you and have a wonderful week.